called poisson distribution, just in case you really want to know how to say it.
Poisson, like that?
Poisson, like a fish.
Oh, that's the word is fish in French.
It is.
Yeah.
Okay, so it's probably somebody's last name. And in fact it is. It is, I don't even know the guy's name. But anyway, something poisson. So he came up with a different method to be able to find probability distribution. And I think this is kind of a cool one. The things that need to work in your favor is that it has to be a constant, let me tell you. So events must occur singly, I didn't even know that was a word before, singly, randomly, and independently. Okay, so for example, at Thanksgiving time, people are cooking turkeys for the most part. People cook turkeys. Do you think that Butterball has a call center at around that time? Like Butterball is a type of turkey, you know? So possibly, like, they want to know how to cook it, how long to cook it, what do you do before? They probably call the call center, okay? So random calls coming into a call center about cooking a turkey, right? Do you think that those random calls occur singly? What does it mean by singly? Like one at a time. So if I call, right, I'm talking to a person, perhaps somebody else is calling, maybe somebody else is answering, but for my one person I'm calling, it would be a single call coming in, right? I'm not creating multiple calls at one time. Randomly. Are those calls coming in randomly?
Yes.
They may start at like 4 in the morning, because that's when, depends on what time you want to eat, what time you want to put the turkey in. Or do you want to wait till like 12 o'clock where you should have probably put the turkey in and you don't plan to have it till next. Anyway, long story short, that happened in our house once. My mother-in-law, her oven broke down. She put it in, she didn't realize her oven wasn't working at like 6:30 p.m. It was still frozen, like it was bad. We're like, not eating turkey. Okay, and then independently. Are they coming in independently? 100%. Those parameters make up something that I can do a Poisson distribution with. Okay, is everybody cool with that? So like binomial, what are my criteria for binomial? That they're independent, right? What else?
Finite.
Finite number of sets.
Constant probability.
Constant probability.
Success or failure.
Success or failure. In this case, I could have however many calls I want. There's no finite set number. Okay, so we'll talk about how that looks. All right, are we cool so far? So those are the 3 criteria. Some of the examples that I've seen are cars at a stoplight going through when the light turns yellow. Are the cars going singly through? You hope so, right? Are they independently going through? For sure, it's an individual car going through, and then randomly, my car goes, somebody else's car goes, it doesn't necessarily be side to side, whatever. So that's another kind of example of an event that could occur. Are we okay? So that kind of gives you some insight as to what that looks like. So the next thing you need to know is the formula, okay? So it's a random variable where we're gonna call it lambda. Lambda is our new, what we're working with. We've used a mu before, we've used a theta before, we've used a sigma before. This is our new guy, it's called lambda, okay? Lambda, L-A-M-D-A, lambda.
Upside down.
Yeah, upside down Y maybe. All right, that is the formula for it. When you have a binomial, you'd have x, little squiggle, binomial, and what are the 2 things that go into for binomial? N and P, right? This is, X is a Poisson distribution with lambda, okay? So, now, this is the way I know it. I wanna see on your bright colored sheet of paper if it looks similar. So on your bright colored sheet of paper, does it look a bit familiar, look similar? Are they using the same letters?
That's what they did.
They did as well? Okay, just wanna make sure. Okay, so that's the formula. And here's what's important to know. What is E of X? Which is also known as the mean. So the mean is lambda. So literally what gets put into this is we're working on with the mean, okay? And the variance of X is also lambda. It's a repeat of itself. The mean and the variance for Poisson are the same. It'll be very natural after I start showing you. The variance doesn't come into play till later, and I'll show you about that. All right, do you have to have this memorized? 100% no. Once I show you an example, you'll see what all the components are and how they kind of fit together, and then I think you're gonna be fine with this. I really do. Okay, so let's do a problem. The number of calls to a consumer hotline Butterball turkey is modeled by a Poisson distribution. If they tell you it's modeled by a Poisson distribution, that means it's happening singly, randomly, and independently, with a mean call rate of 6 per minute. The fact that I'm telling you it's a Poisson means that I can use a Poisson. Sometimes they don't. You have to kind of dive into the problem and figure out, is this something that occurs singly, randomly, and independently? And we'll do some of those as we kind of go along. But just know that when you get to hypothesis testing and you start having to find probabilities, that's when you have to figure out, is this a binomial or can I use a Poisson for this? That's kind of where that happens. All right, are we good so far? So, my X is equal to a Poisson of lambda. What did I say the lambda was? Lambda is the expected value, also known as the mean. So let's go over here and kind of look at the problem. The number of calls to consumer hotline is modeled by a Poisson distribution with a mean call rate of 6 per minute. What is lambda? Lambda is 6. 6 calls per minute. So far so good? Was that easy to pick out? What was my key term that told me it was my lambda?
Mean.
Mean, right. So the mean is. What other words could they potentially use?
Variance.
I don't know what I heard expected value. I heard maybe average. The average number of whatevers. Okay, are we cool? So those are like the indicators. All right, so I want us to find the probability that in a given minute there will be 9 calls. So we're trying to figure out the probability that in a given minute, 1 minute, that there will be 9 calls. So how do I set this up? So let's look at our little formula. It's the probability when, in this case, X is exactly 9. Does that make sense? Because I said 9 calls. So we're going to do the probability when X is 9, it's going to be equal to, and literally we're going to plug into this formula. E to the negative lambda, what's my lambda? 6. So e to the negative 6. And then I have lambda to the r power. in this case, I want to know for exactly 9. So 6 to the 9th power over 9 factorial. And you plug it in your calculator.
.0688.
All right. Have I rocked anybody's world yet? It's really like a lot of plug and chug. Okay. Are we mastering our calculator? That's the hard part. Do we know where the E's are? Trying to figure that out? Help your neighbors. Because Lord knows I have no clue. This one we're gonna do is 3 or fewer calls. What's the probability of 3 or fewer calls? So how does that look? What am I trying to find the probability of actually?
0, 1, 2, and 3.
0, 1, 2, 3 or fewer calls, and 3. How do we know we start at 0? It tells me R can start at 0 and move all the way up to however many you want, okay? So 3 or fewer calls. Now, kind of watch what I'm doing here. Let's see. Can I write over here? Are you guys cool? Can I erase this?
Mm-hmm.
All right. So I'm going to do it the long way, and then I want to show you a little shortcut. So I know we're going to do the probability that x is equal to 0, 1, 2, and 3, right? So my formula is, and my lambda is still 6, right? So we're going to do e to the negative 6, and then it's going to be 6 to the 0 power over 0 factorial, right? Plus, and then how can I alleviate making this as lengthy or whatever the word is? So I'm going to show you. So a lot of people do them individually like such, but what's the one thing that they all have in common if I look across the way? E to the negative 6. So does it make sense that I could write e to the negative 6 and then just do the components of 6 to the 0 over 6 factorial plus 6 to the 1 over 1 factorial, 6 squared over 2 factorial, and 6 cubed over 3 factorial. I could do those individually, add them up, and multiply it just once by that e to the negative 6. Is it wrong if I do it the other way? Absolutely not. Whatever you feel most comfortable and confident with.
Isn't it 6 0 and then 0 factorial?
Oh, that's a 0. I just wrote it wrong down there. Thank you. $151 for that.
Mm-hmm.
I got that.
Most people are pretty comfortable with poisson distribution so far. 0.151, yeah, feeling good? What about the case scenario of more than one call? More than one call. Can. And more than one means what? 2, 3, 4, all the way to infinity, right? So more than one, you're not going to do that many. So you would do 1 minus what? 0 and 1, right? So 1 minus the probability of 0 and 1. Does that make sense? And then I'll give you one more to try while you're waiting. At least one call. One on, right? 1, 2, 3, 4, 5. So what will we do? 0 from 1, right? And you're getting 0.998. All right, how are we feeling? Good? Okay, so let's say you have a typesetter, somebody who types stuff up, okay? On average, has 5 errors per page when typing, okay? So in a book of 200 pages, on how many pages would you expect to find at most 2 errors?
Did I say 5 errors per page in the top?
5, yeah. Okay, can somebody explain to me why we can use poisson for this? What are my 3 criteria? Give me one.
The errors happen randomly.
The errors happen randomly on a page. Does that make sense? Like if I'm typing and my big finger hits, I don't know, E instead of R, right? That's a random error. Does that make sense? Okay, so randomly. Singly, what's that mean?
It's like one at a time, you can't type multiple letters.
So you get one error at a time, one letter incorrect at a time. You can't type multiple letters at the same time. Exactly, I can, but you're not supposed to. Okay, so that's it. And last.
Independently.
Independently. If I get 5 errors on the first page, is it possible I can get none on the next page?
Yes.
Probably not if I'm typing, but yes, right? So you have the idea that independently it could happen. Are we cool? So therefore, poisson. All right, in a book of 200 pages, on how many pages would you expect to find at most 2 errors? So for me to be comfortable doing the formula, what is the formula again? X is equal to R, and then it's what? E to the negative lambda, and then lambda to the R over R factorial. So let's kind of break this problem down into what is my lambda? Average of 5 errors per page. So my lambda is 5. Are we feeling good? And what are we trying to find the probability of?
Would it be 0, 1, and 2?
Because we're trying to find at most 2 errors. So 0, 1, and 2 is 100% right. So we're trying to find the probability of 0, 1, and 2. Beautiful. Okay. So we are going to find the probability of 0, 1, and 2, and then we'll talk about the 200 pages in a minute. Okay? So find the probability that you find at most 2 errors per page, basically, is what's happening. Cool? Yes. All right. Crunch your numbers, my friends. high percentage of finding at most 2 errors per page? 0.125, yes? Yes, 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 no, no, yes? How many pulled the e to the -5 out and did it that way? Yeah, it's a little easier, right, I think? Now, where does the 200 come into play? We found the probability of finding at most 2 errors per page. How many pages are we talking about? 200 of them. So what should we do with that number 200? Multiply it out by the probability of finding it per page. So 200 times 0.125, and what do you get?
24.9.
24.9 should be about how many pages?
25.
25 pages. All right, how do we feel? You can't really have 24.9 pages, we'll just round it up to 25. Cool, I mean you can, but you know, we're gonna guesstimate of the 25. All right, are we cool so far? All right, so here's the dilemma that we fall into play. Right now, what we have is we've been talking about, in all our problems, 6 per minute, and then all of my calls have been talking about per minute, right? Over here, we did 5 errors per page, so all the stuff we've been referencing would be per page. So sometimes it comes into play where you have per minute, and then they want you to compare to half hour, or an hour, or 10 minutes, or 5 minutes. So you have to be able to change your lambda in accordance to that. And they're proportional. So your lambdas are always going to be what we call proportional to the original lambda, okay? So it's always on an interval that's proportional. So let me give you an example. So you have people going into a post office, and the way they wrote this, people arrive into a post office independently and randomly. So does that make sense that it's poisson, right? At an average of, so your average that these people are going into the post office, both randomly and independently. Does it make sense that they're singly going in as well? I am a person who goes into the post office, yeah? Okay. So on the average rate of 2 people every 5 minutes. Okay. So in 5 minutes, 2 people go in. What am I thinking about in 10 minutes? 4 people should go in. It's proportional, right? So the first question says, what's the probability that 3 people arrive in 10 minutes, in a 10-minute period? So we're looking for exactly 3 people are coming in. Does that make sense? 3 people arrive. I'm not saying more than 3 people, not less than 3 people. So the problem is my lambda up here is 2 out of every 5 minutes, right? So does it make sense that 2 in 5 minutes? So my lambda is 2 in 5 minutes. So now I'm going to try to figure out what my new proportional lambda is for this one. I'm working into 10 minutes. So what is my new lambda going to be? Well, y'all said it just a second ago. What's the easiest way for me to get there? Well, this one's pretty nice because 5 goes into 10 twice. 2 times 2 is 4. However, what if they're not pretty? You can't really multiply to get to that next number. What's your best way to figure out what your new lambda is going to be? Does anybody have any idea?
Cross multiply.
Cross multiply. So you would have 2 times 10 equals 5 times lambda. So 20 is equal to 5 lambda. 4 is my new lambda. Is everybody cool with that? Yes? Okay, so we want to find exactly 3 people arrive in a 10-minute period. So my new lambda, so my probability, my poisson is 4 now, right? And we're trying to find the probability that x is indeed 3 for this. So go ahead and number crunch. Let's see how you do. How is this one going? And what do you get for your answer?
0.195.
0.195. Do we like it, or is it not hard, right? Not too bad. Okay, what about the second one? I want to do more than 4 people. Arriving in a half-hour period. So more than 4 people arriving in a half-hour period. Anybody want to volunteer their new lambda?
12.
12, is everybody cool with that?
Yeah.
2 out of 5 equals the new lambda over 30, so 12. Is everybody okay? Yay. And more than 4 people, what would that be? 1 minus 0, 1, 2, 3, and 4, right. It's a little bit of math going on. This test is definitely a number crunching test. Everybody good? Feeling okay about it? So are we getting 0.992?
Mm-hmm.
Point 992? Did you get it?
Yeah.
Okay, I'm gonna give you another. So that was number 2, number 3. Yep. I'll put the next 2 down so you can try them. All right, 2 more to play with. What are you getting for your lambda here? Yes. And what are you getting for your lambda here?
0.4.
0.4. Does anybody need help with getting their lambdas? We're good. Triple I,
0.074. I'm at
point
0.076.
0.0176 or
Yeah.
0.018.
Mhm.
No, not so good.
That's not what
Okay, so let's see.
That's what I got.
You're trying to find 5 people, right? So you're doing the probability of exactly 5 people, right? So it's going to be e to the negative 1.6, 1.6 to the 5th over 5 factorial.
Oh, I know what I did. I put -6 and not -1.6.
Okay,
I knew what it was. I just.
you
put it
just
wrong.
plugged in the wrong thing, okay. So are we good there? Are we okay? And then the other guy is 0.268.
Yep.
Yes? Okay, so,
10 minutes.
I got 10 minutes.
Mm-hmm.
Okay, so you guys understand that we learned binomials and then we convert them to normals. Why? Why would we have taken a binomial and made it into a normal?
Big sample size.
My numbers are too big, my sample sizes are too big. So the same thing can happen here. I can go from a poisson to a binomial. I lied, the other way around. I can go from a binomial, I can go from a binomial to a poisson. Okay? And the criteria that needs to be met for this to happen is that n has to be very large. And your p has to be very small. More specifically, n would be bigger than 50. Okay? And n times p would be less than 5. And by the way, what is n times p equal to? The mean, which is also equal to what? The lambda. So in other words, my lambda has to be less than 5 for this to work. Okay, so let's go. And these are what we refer to as two discrete. So I'm going from a discrete binomial to discrete Poisson. There are no continuity corrections that are necessary. When I went from binomial, which is discrete, to normal, which is continuous, I had to do a continuity correction. Let me explain what that means. So a binomial is I have counting numbers. 1, 2, 3, 4, x is 3, n is 3, n is 5, they're counting numbers. And when I convert them to my normal, does it make sense that we're talking about an array of things that'll fall under a normal curve, to include lots of decimals? So from something that's discrete, singleton numbers, to something that has decimal action going on, that's when I have to start working with continuity correction. But I'm going from discrete to Poisson. I'm looking for something to happen 5 times. I'm looking for something to happen more than 4 times. Do you see what I'm saying? So that's when we don't have to worry about the continuity correction. So let's do a problem. So a company produces electrical components, okay? So past records show that the proportion of faulty components is 0.4%. Is 0.4% small. What does it turn out to be as a decimal?
0.04.
So 0.004, right? It's really small. Does that make sense? Okay, this guy Hari, I think that's H-A-R-I, Hari, right? Okay, buys a box of 1,000 electrical components. Is my number pretty big? We got 1,000. It's rather large, right? Work out the probability that more than 5 components are faulty. So the first thing I do is I see if it meets the criteria. Is n bigger than 50?
Yes.
It's 1,000. Is n times p less than 5? So n is greater than 50 for sure. N is 1,000 times 0.004 smaller than 5. What do we get?
4, I think.
4, I think we get.
Yeah.
Yeah. So it is indeed smaller than 5, and that is my lambda. Are we cool? Yes, no, maybe so?
Yes.
Can you find the probability that more than 5 components are faulty? More than 5? I'm not doing more than 5. What am I gonna do?
1 minus.
1 minus the probability of 1, 2, 3, 4, and 5. Why 5? Because it's more than 5. Did you fall right into line, no problems? 4 minutes, okay. Sweet. Poisson distribution, pretty decent so far. It's actually not hard. I told you the hypothesis testing is the hardest part of stats too. Might as well start with that, right? Most people are like pretty cool with Poisson distribution. I'll put the answer number up here and you guys tell me. There you go. Just when you finish it, you can triple check that you did it right.